Welcome back. This is part 2 of section, what section is this? This is section 5.2. In this section, what we're doing here is we're taking a look at finding the value of an integral, the value of a definite integral here. And we're using a limit definition. All right, so we're going to use the limit definition to find the value of this mess right here. All right, so first off, let's explore what this is really asking us to do. So I'm looking at the notation. I'm seeing the integral symbol here with a lower limit of integration of 0 and upper limit of 3. I'm seeing a dx over here, and I'm seeing a function in the middle. So what this is telling me is that there exists a function out there, f of x equal to x cubed minus 6x, and that if I were to graph that on the interval from 0 to 3, my job is to find the area under the curve. And let's see, if I think about that function, f of x equals x cubed minus 6x. That's going to be x times x squared minus 6. So that's x times x minus root 6 times x plus root 6. Root 6 is what? It's bigger than 2 and smaller than, 2 and smaller than 3. So that means it crosses the x-axis somewhere over here at root 6. To the left of that, see, it crosses at 0, it crosses at root 6, crosses at negative root 6. I'm going to actually go over here and go to Desmos and see what this thing looks like. So y equals x raised to the third minus 6x. And it looks like we are going to be graphing something that is going to be below the x-axis on a big chunk of this interval. So we've got a graph that's coming through like this and going back up. And of course it goes off that way. And our job is going to be to find the value of the definite integral, but our function is sometimes above and sometimes below. Well, this is going to be interesting. All right, so here's where we make our calculus definition of area. You ready? This up here, because it is area between the function and the x-axis, but it is above the x-axis, we're going to think of this as positive area. And then this piece over here, because it is below the x-axis and between the function and x-axis, we're going to think of this as negative area. Right? Now, the reason that we need to think of things in these terms is when we talk about things moving or we talk about applications of this, we need to have the idea of things can increase or things can decrease. So if this was some sort of a velocity curve, then this part down here below would just be where that function was moving left, and this part up here above was where that function would be moving right. And those two green pieces, even though the one below is going to be a negative distance traveled, and the one above will be a positive distance traveled, and so we'll end up with a sum total of the negative and the positive, which will represent how far our object moved total. And if the answer ends up being negative, it just means that the end result is moved left. And if it ends up being positive, the end result means it moves right. Now for my sketch here, it looks like the negative piece is going to be bigger than the positive piece, so the value of this integral should be negative. It is possible to have a different picture where the positive area is bigger, so the end result is a positive number, and absolutely possible to have a picture where the two pieces are the exact same size, but one of them ends up being positive and one of them ends up being negative. All right, but enough of the setup for this problem. Let's get started. Here's what I remember from yesterday. We are going to take the limit as n approaches infinity of the summation as I goes from 1 to n of f of x sub I star delta x, and that this expression right here, this limit, is going to give me the value of that integral. Okay? I need to start laying out some of the pieces and parts here. Okay? I'm going to start out simply by saying, what is delta x? Well, delta x by definition is always b minus a over n, or in this case it's going to be 3 minus 0 divided by n. 3 over n. Now you might be saying, well, what's n? n's a variable. N is the variable from the limit. So n has to stay n. Okay? The next question is, what is x by star? Well, it doesn't say in the problem whether we should use rights or left or midpoints. So I'm going to use rights because it's the simplest formula. And the formula for right says it's always a plus I times delta x, or for this example, a is 0, plus I times delta x, which is 3 over n. Or if we clean it up, we get 3I over n. And there's our delta, our x sub I star, our sample points. So taking these two quantities, the 3 over n and the 3I over n, and plugging them into that formula, I get that the integral from 0 to 3 of x cubed minus 6x dx will be equal to the limit as n approaches infinity of the summation as I goes from 1 to n of the quantity 3I over n cubed minus 6 times 3I over n, all times 3 over n. So all I did is I took the formula for the limit summation and plugged things in. F of x sub I is that first set of parentheses, delta x is that 3 over n on the end. So I'm just making the pieces and parts fit where they need to fit. Now I need to start doing evaluation of this. Okay? So this is going to become then the limit as n approaches infinity of the summation as I goes from 1 to n of 3 cubed is 27 times 3 again will give me 3 cubed is 27 times 3 is 81. So I'm going to get 81 I cubed over n to the fourth minus 6 times 3 is 18 times 3 again. Well, that would be just 6 times 9, so that's 54. So minus 54I over n squared. Right. So if you're wondering where that came from, that was just this all worked out. Okay. And so now this gives me that we have the limit as n approaches infinity. Now here's where the math starts to happen. Okay. I'm going to rip apart, and I'm moving over here, so in case you're wondering where I'm at, I'm talking about this thing right now. I'm going to rip that thing apart at the minus symbol, and I'm also going to use the formulas from before. This is going to turn into two summations. The first summation is going to be 81 over n to the fourth times the summation as I goes from 1 to n of I cubed minus 54 over n squared times the summation as I goes from 1 to n of plain old I. Right? In the summation, the variable of the summation is the I. Everything that isn't an I, we're pulling that out. We're factoring that out and putting out in front of the summation. The reason we're doing that is these two summations now can be replaced with those formulas that we memorized yesterday. So I'm just going to scroll back up here to remind you of them. There they are. So we're going to use this formula for I, this formula for I cubed. Right? So stare at those for a second, burn them into your retinas. Here we go. Right? So now this gives us the limit as n approaches infinity of 81 over n to the fourth times I cubed became n squared times n plus 1 squared over 4 and minus 54 over n squared times n plus 1 over 2. Okay? So I'm going to draw some arrows here so we can see what became what. Okay? The I cubed is right there. The I is right there. The coefficient's still there, and that coefficient's still there. Okay? Now I just need to take the limit of this business. Okay? What do we got here? So then, and I'm going to steal some space down here from this next problem because I ran out of space, unfortunately, and I can't make this text go lower. But this is going to be equal to, and I'm going to take the limit as n approaches infinity. Since this minus sign here in the middle really makes this two terms, I'm going to find the limit of the first piece, then I'm going to find the limit of the second piece, and work those independently. The first one, if we distributed everything out in that numerator, we would have 81n to the fourth as our leading term. We'd have 4n to the fourth in our denominator. So the limit of that first term would be 81 over 4 minus. If we distributed everything out in the second term, we'd have 54n squared over 2n squared, so then minus 54 over 2. I'm going to grab my calculator to evaluate that. So that's going to give me 81 divided by 4 minus 54 divided by 2, and I get negative 27 fourths. Negative 27 fourths is our final answer. So that tells me that the area under this curve, or the area bounded by the function x cubed minus 6x, and the x-axis on the interval 0 to 3 is negative 27 fourths. Negative because there's more below the x-axis than there is above the x-axis. So what we're looking at here is we're looking at a situation where we have a curve that is sometimes negative, sometimes positive on our interval, but the area between the curve and the x-axis that is below the x-axis, the negative area, is just larger than the piece above. Okay. If you want to put this in context, if this was a particle moving left and right, the end result is it moved further left than it did right, so it ended up left of where it started. Ended up left by 27 fourths units, whatever those units would be. Right? Now, I know that's a lot to digest, so you can probably rewind and watch this several times to make it work. Right? All right, let's take a look at the next example. It asks us to evaluate the integral by interpreting it in terms of areas. Okay. So what does it mean to interpret in terms of areas? I'm not sure, so I'm going to make a sketch. I'm going to make a sketch of what this means. All right? So what this means is my function is y equals x minus 1, or f of x equals x minus 1. My interval is negative 2 to 2. Well, if I make a quick sketch of that, this is a line with a slope of 1 and a y-intercept of negative 1, so it goes like that. Crossing here at negative 1, crossing here at positive 1. My job is to find the area between the curve and the x-axis starting at negative 2 and stopping at positive 2. And so I don't know about you, I'm hoping you're seeing the same thing I'm seeing. I'm seeing a triangle over here that is below the x-axis and a triangle over here that is above the x-axis, and it looks like the yellow one, which is going to be our negative area, is bigger than the blue one, which is going to be our positive area. Now, I could use limits and do all that, but considering that we've got a line here that made perfect triangles, I can just use geometry. Right. So this triangle over here on the left, the negative area one, what's its size? Well, one side of it is 3 units long. The other side is, well, how long is this side? Well, what's the y value there? Well, the y value there is negative 3. How did I get that? I put negative 2 into the equation. So that means that this side is negative 3. So then the area is going to be 1/2 base times height. And I'm going to say height in quotes here because we're actually talking about negative. Right? which means it's going to be 1/2 times base of 3 times height of -3, or -9/2. How about the positive piece? What's going to be the area of the positive piece? Well, the formula is still 1/2 base times height. Well, if this is 1, then this side over here has a length of 1. And this point right here, if I take 2 and I plug it into the equation, has a height of 1. So it has a base of 1 and a height of 1. So it has an area of 1/2. And then the sum total of my two areas is going to be our -9/2 plus our +1/2, which is -8/2, which is -4. And so I got a sum total area of -4, or the integral from -2 to 2 of the function x minus 1 dx is equal to -4. Now, why don't I just do that every single time? Why do I need all this fancy math? Well, the only reason I can do it for this one is because geometry didn't fail me. I can make perfect geometric shapes because the sides of these are line segments, which means geometry's out there, find the formula, plug it in, grind it out. When geometry fails me, that's when I need this. Okay? All right, some properties of integrals. Let's take a look at the first one. The first one says the integral from a to a of f of x dx is equal to, a to a will always be equal to 0. And why will that be equal to 0? Why is that such an ugly 0? Why will that be equal to 0? We'll take a look at this. What does this tell me? You're starting at a and you're stopping at the exact same number. To have area, we need both width and height. And if we have no width, we have no area. Okay? The second property over here on the right says the integral from b to a is equal to the opposite of the integral from a to b of a function f of x dx. So what does this one tell me? It tells me that if I want to switch the limits of integration, these limits of integration, I can do that as long as I put in a negative. Now, why would I want to do that? I'm not sure yet, but I know that I can. I can change the upper limit to the lower, and I can change the lower to the upper if I'm willing to put a negative in. Now, there are many reasons why you might want to. What if there was a negative in your integrand and you wanted to factor that out? Well, you could factor out that negative, flip your limits of integration, and then not have to worry about that negative anymore. So that's one example. The integral from a to b of f of x dx is equal to the integral from a to c plus the integral from c to b. So what is this one saying? Oh, if I want to, I can take an integration problem that starts somewhere at a and stops somewhere at b, and if I want to, I can split it up by picking a c in the middle, find this piece, that would be the integral from a to c, then find this piece, that would be the integral from b to c, and then when I add those two together, I'm going to get the value of the integral from a to b. Now, the thing you should keep in mind with these is this is an equal sign, which means the left could turn into the right, or the right could turn into the left. Right? So if you happen to have a situation where your integrands were the same, you could put limits together properly and make it into two integrals into one integral. Right? Unfortunately, I need this space over here, so I'm going to have to erase this most beautiful picture that I just got done drawing. But I can do that. Right? All right, our next property says, what do you do if you've got a coefficient right there? Well, just like with derivatives, just like with antiderivatives, if there's a coefficient that you don't like, pull it out and deal with it later. So if you can factor a number out of your entire integrand, you can factor that number out of the integral itself, find the value of the integral, and then multiply it by that number at the end. So if there's a horrible coefficient you're not liking, like pi or the square root of 5 or something like that, if it's in all the terms and you can factor it out, factor it all the way out, call it good, deal with it later. Okay? It's one of those nice things about integration. Last one down here at the bottom, what do you think is going to happen here? Well, I've been given the statement, the integral from a to b of f of x plus or minus g of x. What I can do is I can write that as the integral from a to b of f plus or minus the integral from a to b of g of x dx. And basically what it says is, if you want to, you can rip an integrand apart at addition or subtraction. Or, if you're working from the right side pink to the left side black, if you have two integrals with the same limits, you can take those two integrals and write them as 1. Okay? All right, properties of integrals. We're going to evaluate. This will be the last one for this video. We'll move forward from here. We are asked to evaluate the integral from positive 1 to 3 of the expression using the following statements. The first statement says if it was just plain old x squared, the answer would be 26/3. The second statement says if it was just the plain old integral of x, it'd be 4. And the third one says if it was just the plain old integral of dx, it would be 2. Now remember with that last one, what's hiding in there? If you zoom in, you can see it. When you zoom in far enough, do you see the 1 that's hiding in there? 1 times dx. All right, keep that in mind. All right, so how am I going to use those three truths, these three truths right here? How am I going to use these three truths to evaluate the given integral? Well, I'm going to make use of the properties up above. First off, I need to rip this thing apart at those two. So I'm going to say this is going to become the integral from 1 to 3 of negative x squared dx plus the integral from 1 to 3 of 4x dx minus the integral from 1 to 3 of 3 dx. Now I'm looking closer. This one now looks a lot like this one except for that stupid negative. Ooh, but I know how to deal with that. That negative really means a -1, so let's just pull that coefficient out in front. And so that's going to give me -1 times the integral from 1 to 3 of x squared dx. And now my integral matches, and on the next step I'll be able to replace that with 26/3. Moving to the second one. Well, these two almost match except for that stupid 4. But I can just pull that 4 out in front, and now I've got plus 4 times the integral from 1 to 3 of x dx. Right? Moving on to the last one. Hey, these look a lot alike, except for this is a 3 and that's a 1, so I'll just factor that 3 out. And I'll get minus 3 times the integral from 1 to 3 of 1 dx. And now that I've done what I've needed to do to make this one match this one, and this one match this one, and this one match this one, I'm going to replace each of those with their given values. That is, the first expression will become -1 times 26/3 plus the second expression 4 times 4 plus the third one, actually minus the third one, minus 3 times 2. So -26/3 plus 16 minus 6. I don't know what the heck happened there. Let's see, -26/3 plus 10. What is that going to be? 4/3 when it's all said and done. And so I use properties of integrals to rip it apart and evaluate each piece independently. All right. I'm going to end the video there. We'll come back and take a look at this one, which looks a lot like a test question to me. I'll see y'all back here for 5.2 part 3.